I realize this is the last presentation in this session, which means you all got nothing else to do, so we might just as well stay for a couple more hours here. I'm kidding, actually. I'll try to confine my presentation to the time slot available, although I usually fail at doing that. So I'll probably have to skim through some of my slides. Now, ladies, gentlemen, my name is Igor Kotenko. I'm with St. Petersburg Academy, which is part of the Russian Academy of Sciences, and I've been an expert in information security for quite some time. And in this presentation, I'm going to report on the research I've been doing for a number of years. In fact, I'm going to report on two major international projects I was involved in. In fact, in previous positive hack days, I talked a lot about these two projects. One is called Positive, the other is called Massive. We are now running four projects for the government or for the public sector, and they have yielded some results and some insights that I'm going to cover in this presentation as well. Are we talking SIEM projects? Well, yes. I will be mostly talking about metrics, while these projects are mostly about incident monitoring and management, but there will be overlaps. And although I'm the only person presenting to you today, obviously a lot of work has been performed by a number of people working in my lab. I'm wondering whether Yelena Donnikova is in the room. She's doing metrics for this project. For visualization, I like to point out the contributions of Novikova, Mrs. Novikova. While for events and attack graphs and vectors, Andrei Chichulin would be the person to point out. Although, by the sound of it, more people were involved. Well, this agenda will be, I'm sorry, this presentation will be purely academic. I'll first tell you about the problem, then I'll tell you what is usually done in this respect, what makes our approach novel, and then we will look at some insights and conclusions. A fully academic presentation should also include a review of things that could be done next. Now, if you're an expert in this field, you might be interested. I'm sorry, since it's an academic presentation, I have to start out by giving you some common terminology. I do not expect I will actually tell you anything new in this part of the presentation, but just in case, I need to do that. After that, we'll briefly discuss different approaches one can take in order to calculate metrics. After all, there are too many, or at least a lot of metrics. We'll only be considering the metrics that correlate with what I call institutional awareness. I will discuss it in more detail later. In this chapter, we're going to discuss different metrics, how they work, how they can be calculated and measured. After that, we shall talk about metric visualization, because calculating is all very well, but without visualization, the benefit will be very limited. Because in real life, it's very important to make sure that an analyst or a security manager or admin finds it easier to monitor the whole perimeter, to monitor all the potential vectors of attack, and actually react quickly. I will finish my presentation by describing potential follow-up experiments. Let's look at the definitions first. If you browse on the internet, you will find a number of very good presentations, for example, by Andrei Lukatsky, and he provides metrics in depth, but I mostly care about institutional awareness metrics. Therefore, I will mostly care about metrics that can be used for monitoring and those that will support decision making. Shown here are all the questions that you will want to be able to answer if you have indeed a distributed system exposed to diverse attacks, both internal and external. Well, in such a system, for example, you might have users generating illegal software or bringing their portable devices and USB sticks and what have you. So if you have well-defined metrics, you should be able to answer all the following questions, like what are the vulnerabilities, the key vulnerabilities in the system, which of them are critical, which should be eradicated in the first place, is your system being attacked right now, which particular component, be it a system or an application or a service, has been or will be compromised, who is attacking your system. It's important to attribute the attack to somebody in particular. How can we measure the potential risk of the current situation if no attack is being performed or the current attack? What is the most probable target of the attack and what is the exposure? How can we prevent the attack? Or is the paranoid termination of everything the only remaining route for us? What are the potential responses? Because usually you have alternatives, not just the paranoid switching off of everything you've got. It's important also to ascertain the amount of time it will take you to mount a response to an ongoing attack. So we need to go for the optimal route, so to speak. What kind of computational resources will be exposed to the attack? What will be the potential damage? This is in fact a way for us to gauge whether business continuity is going to be endangered during our response or not. Well, this is a toy example for you. Well, this could be a host or applications running in a single host. But in any case, you have a system. Inside the system, you have nodes. In fact, these circles could even represent individual vulnerabilities. It doesn't really matter what you encode into the system. What matters is different, that you get your information coming from the sensors, you process it. You're looking at some particular node, shown in yellow here, which is currently exposed to an attack. There are some inputs and outputs in every system, including this one. There are some critical resources as well. Now, based on this multitude of questions, a good SIEM system should enable us to automatically, or at least semi-automatically, produce quick and reliable answers, because obviously you don't want your experts to manually crunch all that. When done properly, the system should provide you with most of these answers straight away. And then it would fall to the operator to select one of the proposed responses. Or he could run some what-if scenarios and select something that fits better. So let's assume that some preceding events show that, well, for example, several nodes were compromised before that. This is a way to read this particular chart. Well, in our example, what you see over there is that we haven't registered uh, any attack on the second circle, which means that either our sensors are not reliable or it was a 0 day. Now we're assuming that this is the node being attacked at the moment, and you will see there are multiple arrows leading out of the yellow circle. And again, if you build some brains into the system, if you're using this matrix, it will be easier for you to predict which node will be the next target. After all, this is why we need matrix. Well, because many people say, metrics are useless, they don't tell you anything, but in fact, when they can be used as predictors, they can already be worth their money. After all, you cannot always ensure that it's only the experts who are manning your system, and it can be quite difficult for them to keep the whole system in their mind, particularly if it's a geographically distributed, humongous system. Okay, now that I've covered metrics, we're going to discuss where these metrics are going to be measured, calculated, used, processed, and visualized in a SIEM system. Obviously, we need to be proactive when we do that, because usually attacks don't last for years. And on the other case, when you accumulate all this information in an SIEM system, a system administrator, for example, will be able to keep upgrading the system, patching up vulnerabilities, for example. So we are providing here an extended list of objectives for an SIEM system, which includes upgrades, among other things. Okay, what we're showing here is a multitude of sensors that are involved in data collection, data management, data analysis. There are different ways to reaching this objective, but we're not going to cover them. They're not the focus of this presentation. So you see that at the bottom level, a wealth of data is generated, but most of it can be junk for a particular research purpose. So we need to filter out the stuff that is less relevant. Shown in red is the focus of my current report. Because obviously you can use your metrics at different levels, but we mostly need them for the analytical part of the pyramid, the top one. And the stuff we're listing there includes visualization, decision-making, setting priorities, and analysis of events, incidents, and their potential consequences. The magic quadrants. As usual, we have leaders. These were leaders for 2014, and this must be the emerging leaders for 2015. Well, interestingly, the stuff that I really care about is pretty weak, even in the products of the leading vendors. Shown here is a generalized architecture of an SIEM system, and this is exactly the architecture we used in our latest project. This is a high-level representation of it, so we have data level, collection level. We also have a high-speed data bus, and here we ensure that all the events are properly analyzed. Well, in fact, the data bus is not just a conduit for information, it's also where information gets stored. So this is where events get processed here and there, and next we assess the security level. Next we have decision making, visualization, countermeasures, and the whole thing reiterates again. In order to have metrics, in order to properly calculate metrics, you obviously need to have underlying models. Usually these models are called attack models and countermeasure models. And listed here are the reasons for having those models in the first place, but they're sort of self-explanatory. When you have a model for an attack, it's easier for you to predict the next target. Correlation of individual security events would be another objective. You can in fact talk about multi-level correlation. I'm in fact referring to high-level correlation when all the events have been collected, when you've normalized, cleansed the data, and when you feel that, okay, you're lacking some events for a full picture, and on the other hand, you understand that some data could be extraneous, unnecessary for the needs, for the purposes of the follow-up analysis, which means that you have to deal with data redundancy. Again, most of these problems could be sorted out through automation. Well, next, you calculate the protection or security levels, and other objectives could include development of the right set of countermeasures, among other things. Let me give you some bibliography here. Well, these are in fact some fundamental works in this area. Model checking originates from some of these fundamental papers. Well, model checking often involves browsing through a number of options and variants and eradicating the dead ends. So we have expert systems, conditions and preconditions. Again, lots and lots of good publications on that. A logical approach. Prologues and data logs are based on them. It's where logical computation is heavily used. Well, in fact, it's pretty similar to expert systems, however, the logical approach is slightly different, and in a way it's more classical, because they apply both the resolution principle and the conclusion principle, and finally, attack graphs, in fact, attack trees, because attack graphs, they would be cyclical, and that would be more complicated, while attack trees essentially the dumbed down version of attack graphs. Maybe that's what made them popular. Next, we are looking here at attack scenarios and perp models. A very important concept, in fact. And I'm mostly talking here about Western American models, to be precise. Not a coincidence, really, given that the guys seem to lead the world in this respect. So for national security purposes, we might probably need our own models, but they will take time to develop. So what I'm showing here, for example, is specs and standards for platforms, vulnerabilities, vulnerability assessment, attacks, weaknesses, and configs, and you know all these abbreviations. Security metrics, there are lots and lots of great publications on combining dependency graphs for services with attack graphs. Well, you see what the idea is here. You see how a particular attack graph will propagate in a particular system. So, for example, your countermeasure that would ban a particular vector of attack would thwart the attack in a different direction And a good system should actually show where you're going to by channeling the attack to a particular route where you might endanger your business continuity SLAs. So you need to see the service dependency even when you are trying to protect the system from an attack. An extremely important group of papers deals with zero-day attacks. Not knowing anything about them is not good enough. It's important to have at least a rough understanding of which particular elements of the system could be more exposed to potential zero days, even if we don't know much about them. It must be part of your model. In fact, there are models like that. There are tools that might help you, and I would love to read an hour-long presentation on that, though we don't have the time, unfortunately. Modeling countermeasures. Again, they will use graphs mostly for that. It's also important to discuss metric classes. Again, classifications are numerous. I can easily take an hour describing different ways to bucket those metrics. Well, quite often, the classification used is topological. Again, I'm quoting some fundamental papers. Like this report, for example, contains a very long list of these metrics. This, in fact, could be the biggest impact of my presentation. If you have little interest in this field, or have had little interest in this field before, it could give you guidance in terms of what to read for the next month or so. Okay, these are subclasses as well, and again, I'm giving specific examples of these metrics, which unfortunately we don't have the time to read. Another classification would deal with the metrics of the perps, because indeed it's quite interesting, in many cases very useful, to have at least a rough understanding of who you're dealing with. Is it a script kiddie, or is it a state, which is essentially an APT? We've heard today already that it's very easy to ascertain what kind of threat you're seeing, but in fact, sometimes it isn't. Attack and countermeasure metrics. We've mentioned that already. You see a particular point in your graph and you want to know what's going to happen next and what will be the consequences of the next attack. There can also be some integrated holistic metrics, or system-level metrics as they're also often called. They give you a general reading for the whole system and its current health state, if you like. Now, when you see the high-level picture, it is easier for you sometimes to drill deeper into a particular issue, like somebody keeping a USB stick in their desktop, or a particular application being compromised. So admins will be drinking coffee and watching TV while all those fancy visualizations play in their screens. And then they see that a particular metric has changed color, and that should trigger his attention, and he should drill deeper. Compare it to him simply getting a notification that something has happened. Now, if you do not provide enough details, it could be difficult for a less experienced system administrator to quickly predict which other elements of the system could be compromised next and what kind of exposure at a systemic level we're talking about. I'm not saying we are there yet, but this is where we should be. Cost-benefit analysis is also very important. This is what most organizations will care about, like how much it will cost you in order to deal away with a particular threat. And I've mentioned already zero-day vulnerability analysis. This is something that gets researched a lot today. I assume this is something that you know, right? This is a good metaphor. We are talking about standards. I'm not going to provide you with an in-depth description. Let me simply explain that CWE, CAPEC are not shown here for no reason. We show a particular vulnerability and a particular vector of attack. Let's take at Mitra. Now, they have lots of protocols, and they also have lots of standards. Now, we need to consider a particular SIM system, so let's consider Mitra for the moment. You see, there are lots of functions here, such as assets, discovery, and stock taking, if you like, inventory, and so on and so forth. Enumeration, analysis of vulnerabilities, analysis of configuration management, and so on. A proper SCAP will contain the following components. We need, for example, to know which vulnerabilities exist and what kind of config vulnerabilities we should be aware of. So this means we need to have access to this database. We also need specs for state controls and control checklists and what have you. Shown here are lots and lots of other standards and protocols. I haven't even had the time to mention them, but obviously you will need most of them. This goes for MAC and CAPEC and CWEs. So all these platforms and standards that are used in SCAP, they're all designed to answer specific questions, like which particular vulnerability we need to be aware of, or how do we set priorities, or how do we calculate our metrics, and we have standards answering all those questions. I've mentioned 0 days, right? And this is a methodology for that particular case. Because weaknesses and the least of those, CWEs, should give you an idea of where 0 days can potentially appear. So when you calculate or when you predict vectors of attack, there's something to keep in mind. CVSS, Common Vulnerability Security Scoring, is an extremely important standard. I assume you've significant knowledge in this area already. For attack graphs, for example, it is very, very important to take into account access complexity. In order to make decisions or support decision making, two other standards will matter, CRE and ERI. Well, in fact, ERI is the extension of CRE. So you'll see we have this multitude of different entries, and each of them covers a range of things you can do as countermeasures, essentially. ERI adds lots of links to other standards such as CPE, CVE, and CCE, provides prerequisites for countermeasures, so it could be in fact a reliable standard to support decision making. What we see here is a range of scanning tools, and then information on CCEs and CVEs comes from them, while CRE and ERI are used over there in order to support decision making. Now, this is not just a logical layout. A system like this has already been created. It's a shame we have so little time, really. I wanted to tell you about some general metrics that are general but interesting in a way. So in order to assess at a high level the general state of the system, they could be quite good. Well, for example, attack surface can be assessed like that. Or attack depth, a weighted attack depth. A system immunity level would be in fact the inverse of the attack surface. If it's a fast attack and you have a large system, say you're a large corporation or a big country, this one will show the speed of propagation, AES. So indicators like this can be very useful for, again, top-level representation or speed of propagation at the root level. NUDI, TUDI should be total impact on downtime, right? SRTs, average recovery times, and so on and so forth. These are well-known indicators, but I must mention them. Vulnerability density, weighted vulnerability density, and so on. Okay, business impact risk should be weighted again, I think, is another very popular metric. I'd love to give you more details, but let me just give you a single example that should flesh some of these items out. I remember that mayor ran a collection of workshops on metrics. So every host could be represented as a set of services and vulnerabilities. We have this metric called exposure, the other is business value and risk. So when you multiply business value by exposure, you get risk. This would only matter to a particular host. What we care about is not an individual host, but rather a chain of hosts. Remember my initial picture. We can actually take into account the number of vulnerabilities, the distances between them, and we can arrive at a kind of comprehensive exposure metric for the whole system that gives you a holistic measure of exposure for different chains of hosts and their exposure to different vectors of attack. Attacker skill level is something I also mentioned previously. There are several ways to measure that. In some cases, we can attribute professionalism to a particular action or chain of actions, or alternatively, when you see, say, a chain of events with missing links. A missing link means you're dealing with a 0-day, and this means you're dealing with a professional. Even if he bought the 0-day exploit, that means he's a professional. Now, the first approach is when you measure the professionalism of the attacker looking at a single action, or you can be looking at a chain of actions. And the third approach is when you're looking at non-action, so to speak, or something that should be there but you haven't registered it. Again, we can be measuring attack impact statically, or dynamically. This is the more advanced way. That way, you will actually be looking also at dependencies, service dependencies primarily. There are different ways to do that, but the underlying idea is the same. As new events occur, the system runs over and over again its own calculations. Response efficiency should be the last metric in this chapter, because it's nice to know whether you are mounting efficient or non-efficient countermeasures. I'm only showing two financial measures here. Obviously, there are many more, but we are not a business after all, right? We want to simply measure the efficiency of our security systems. So this is return on response investment. And by the way, we worked with these guys in one of our projects. And you see, they slightly tweaked the formula. They added annual infrastructural expenses. So that's somewhat distorted the classical formula. Now, this stuff I reported on previously several years ago, so I'll go very quickly. The idea is that we're adding this component to a traditional superstructure, to a traditional SIM system, so that we can actually measure the efficiency of metrics. So we can be using, for example, a security repository, and we'll be having, for example, service dependency data and metrics and so on. A range of diverse security indicators can be calculated. We discussed some of them. And we can also have this stochastic probabilistic approach for predictive analysis purposes. So these are different tools we can use in order to generate attack graphs, to analyze attack graphs, and most importantly, to support decision making. Well, first, we calculate those graphs in the existing configuration, and when the system is already up and running, we will adjust and adapt those graphs, which means that we won't be building graphs from scratch. We'll fire up an existing fragment of a graph, but then we will have the option of modifying it. And that's why we mentioned that we have these two stages here. I'm showing here the static and dynamic modes, where graphs are redrawn essentially. That was the more blown up, so to speak, system structure, system architecture. Okay, shown here are the real sensors that do the monitoring, that submit the monitoring information. For example, we learn there is an attack on a particular node, and it's instantly shown in our model. Set of indicators. Yelena Donnikova, is she here now? This is her work, essentially. So we are showing here all the main groups of indicators, the sources of those indicators, and the integral indicators as well. Integral indicators are the ones that admins are looking at while they're sipping their coffee, while they believe everything is fine. Helpfully, names of the metrics are in English, because this is how we designed it all for the project. We've covered the most important ones in any case already. There are several different methodologies used in order to calculate security measures and indicators. Some can be statistics-based, if you like. No, it must be static, not statistical. I'm sorry. So static, which means that they sort of give you a prediction, right? It can be used beforehand, while dynamic ones are more important when you are actually experiencing an attack. Well, you see here the host vulnerability metric, and you see it's pretty simple. It comes from CVSS. You select on the host system the vulnerabilities that are considered critical. You will remember that in it must be CVSS. Criticality is from 7 to 10. Scores from 7 to 10. And then we run normalization. We calculate weaknesses in order to take into account potential 0 days. Host criticality as well. Confidentiality, holistic completeness or comprehensiveness, and accessibility are the key three measures. And attack potentiality, again, we're using the WISE formula here. Decision-making metrics that are usually relied upon when you need to develop countermeasures. They rely on CRE and ERI. And these are the usual fields. You have, for example, name of a measure, which group it belongs to, next its description, an example, and so on. Platforms, vulnerabilities, implementation, impact, scope. So these are all the attributes that you need to take into account in decision making. And next we bridge the model for countermeasures to the attack graphs. And such a model will show how your particular countermeasure is going to thwart or divert an attack. I made a major presentation last year on visualization, so I'll briefly remind you what it was about. It's indeed important to visualize the way security rules work for the administrator so that he has no doubts at all what is and what isn't allowed. It can be shown in graphs. It could be shown in this embedded nested trees. Or you can just read your firewall rules, but you gotta agree that this way of visualizing the data is actually better. We can represent events and vulnerabilities like that. What's nice about it is that you see it for the previous 24 hours, right? And what's nice about it is that it also adapts to time of the day. It will turn black during the night. It stays white during the day. Okay, shown here are attack graphs. Okay, SIEM, I assume you know it. This is the semaphore representation of risks. What's bad about it is that we only see a single metric, and you would probably want to see a comparison and see how it changes over time. And you either have to go through the whole hierarchy checking for this information, or you have to develop a script or something that will do that for you. Well, there are in fact some interesting proposals. For example, Erbacher came up with a very nice model. Clock face model, I think it's called. So later events are usually shown on the periphery of the circle. Marushak, you know this VIS circumference run in the United States. And this is one of the best works they produced, I think. In fact, we used both ideas in our project, and we in fact even built on them. So the way it works is that they show different metrics in different sectors of this circle. So if you have, say, 4 to 10 metrics, it's pretty easy to show all of them in a single chart, and an admin can react pretty quickly to it. With a little bit of training, the administrator should be able to react very quickly. Now, if you have a greenhorn manning the system, it will be different. But an experienced operator will react very quickly. So we actually played with it and tried representing it differently. You see, there are several attributes here. So the bigger the rectangle, the higher the criticality, while the color denotes the level of exposure, if you like, whether it's a serious weakness or not. So Yevgenia Novikova proposed the following model. She said, why don't we take the Matasak model, split into several sectors. The current state can be shown in the center, and older states are shown closer to the periphery. And you can also play with the size of the sector. And she also had the idea of using color coding. There shouldn't be too many colors, right, to make sure there is no confusion on the administrator's side. Well, this is what I previously mentioned. Attack probability, attack impact, plus criticality level. We're only talking about 4 indicators here, right? This is exactly how many indicators you need for situation awareness purposes. So you need to know whether a particular part of the system is being attacked and what kind of probability, whether a particular vulnerability exists, what will be the probability of an attack, what will be the exposure. Shown here is a potential glyph you can use in order to represent RORI measures for diverse countermeasures. You might say, why do we need a fancy circle like that when you can just show a table? You know what, I've been to Japan, and at a conference in Japan, they showed a research system. It's essentially kind of an experimental dashboard for a nuclear power plant. Do you know what it looks like? A cow in a pasture. And, you might think, what has this all got to do with a nuclear power plant? It was a research experiment, but you know what? It was actually quite good at encoding the information they had. They had like 1,000 different parameters built into it. This is what might look like in a particular network. What if you have a large network, a distributed network for smaller networks? You can show a particular host as a glyph. Now, for large networks, you won't be able to show all the links between them, and you will only be showing individual nodes and hosts, but then you can drill deeper into the ones you care about. Okay, this is what it would look like for a small or medium network. This is what it would look like for a bigger network. So links are lost, but as a exchange, so to speak. In return, you have the visibility of the whole system. So here is the general architecture for one of the prototypes. It's traditional, really, not to say cookie cut. Let me talk in detail about the visualization component. What's nice about it is that it enables you to connect other components of the SIEM system. It also supports the use of information from different components for visualization purposes. It was produced as part of this project, and different partners developed their own components, so it was very important for us to know all the interfaces. I'm just showing you several graphic interfaces. Okay, shown here are the integral indicators, I'm sorry. So the moment you see red color there and you're the system administrator, you understand that the coffee time is over. Now you see Property Explorer, Network Explorer. This is the topology we discussed previously, and you can represent your topology differently. It can be done like that, or like that. Or you can be showing a tag graphs there. That would be a different topology layout. So again, we're using color coding here. And this was the particular GUI that we used. Aitos was one of our partners, and you probably know these guys are responsible for the information support during Olympics. So we in fact recreated the structure for the Beijing Olympics. So we have the external segment, DMZ, we have the Olympic Games network, the internal network for the wireless devices. So the system that is used by the journalists, it's also used to sell tickets and provide information on individual tournaments. Say core game system would host the accreditation server where all the key credentials will need to be maintained. We have firewalls and what have you. It's pretty boring. Skim through it. We played a bit with vulnerabilities there. We decided to use funnier software to have more fun with it. And this was the initial level of vulnerability or security of the host. But after we reconfigured the network, it changed to something like that. Now you can compare the two pictures. There are different ways to do your visualization. So we performed a psychological experiment on usability, and there were several operators involved in the project. So they played with the interface, and they said, well, indeed, it's much better than what we had before. And they say, well, we should make it part of SIEM. It's not happening yet at the moment, though. I'm wrapping up now. Right, this is an academic presentation, so we need a conclusion part. Okay, I covered the current state of affairs in this industry. I gave you a listing of all the tools and methodologies that exist in this area. I also provided a kind of comparison. I also presented our own solution. And it has the following benefits. First, it enables you to assess the overall state of the system. It also supports proactive monitoring, and it supports decision-making in terms of developing countermeasures. Well, you can also play with what-if scenarios. You can actually simulate on the system whether a particular countermeasure is going to undermine business continuity and whether it's going to thwart an attack or not. There has been a number of publications. Well, for example, this presentation will be available on the website, so I'm not going to list any particular references here. Most, you will notice, of these publications are in English, but some are also available in Russian. So we are going to continue developing and upgrading our model. We want to implement it in our standalone project as well as in our joint collaboration projects. We're also trying to develop our own tools that will help others measure the efficiency of SIEM systems. Okay, shown here are all the details, contact details, a list of projects we're working on now, and also the thank you list. Thank you very much. I'm not sure I have time for questions. I'm Konstantin from Severstal. Understand? You rely on some data sources to get your metrics. The problem most SIM systems have is that you never see the real picture. I mean, there is so much white noise. And I understand that the system you're telling us about is essentially research, it's experimental. Well, we have several prototypes. Individual components have been delegated to partners. I don't know whether they're going to transform them into commercial products or not. Have you done any value contribution research? I actually mentioned that in my speech. This is an automatic output system, right? I accentuate and I emphasize the metric part of the story, but in fact, you can see it as a subclass of automatic output systems, and they all have a kind of a birth defect. First is the quality of data you're using, and the sufficiency of data you're using. No, whatever system you're using, remember, GIGO, garbage in, garbage out. You can have the best system in the world, but if you fit it with trash. What's also important is that we make this assumption that the data we are using will be relatively good. We have an underlying assumption that some data might be corrupted, some data might be lost. So a certain margin of error is built into the system, but generally we rely on data quality. I actually wrote my PhD on how to process insufficient information, so I can easily go off on a tangent here. Now, for example, if you've missed a message, be a particular, event notification, right? It's not there, but you can still see like a string of others. It's easy to reconstruct when you have too many false positives. It's indeed an issue for the whole system because it might distort all your correlation analysis. So, to answer your question directly, our system is based on the assumption that data is generally reliable. Okay, you've been mostly telling us about the short-term implications. How about long-term? Well, this is mostly a short-term application. It should support short-term decision-making. It is the primary function. However, there are two modes, offline and real-time are the names. Offline could in fact be used to support long-term decision-making. For example, you can maintain in the system all your constraints and experiment with alternative system designs and see how much they will cost you, what will be, the overall level of security provided, and so on. But again, let me reiterate, the primary function is to support on-the-fly decision-making when you need to counter an attack. My first question is about false positives. I understand most false positives result from ad hoc decision making, mostly by the analysts, not in the systems. In other words, false positives are judgmental, so probably don't even need to find them at the system level. That's right. I did mention that we make this assumption that correlation routines do a good job, which nobody really guarantees. So we must make assumptions that will be contrary to this one, really, that sometimes these correlation models will fail. What about long-term attacks? Well, for example, if there is an APT happening at your infrastructure, will your system be good at helping you analyze it all? Because you can log all this security events to some ARC site or whatever. This is exactly one of the functions of the system, sure. It doesn't really matter for how long the attack persists. You know what I talked about when I said offline mode? Now, offline mode is something you will need to make strategic decisions about how you will develop your network. I can barely hear what the guy says. Well, much will really depend on how you develop your output models. For example, if you have, say, a month before the attack will start, you will be able to build into the system additional measures. I'm sorry, gentlemen, there will be another event in the same room in like 2 minutes. Oh, good. So this puts the lid on this particular session, but Mr. Katenka will